Hello everyone and welcome back to our tutorials. Today I'm going to show you how to take a data frame and break it down into its various parts and see how to reference those specific parts of the data using conditional operators. So I'm just going to be using the data file that I brought in from Excel in the previous episode. So if you haven't seen lesson 4, you'll need to watch that if you don't already know how to do this. I'm just going to call this data as I have been, and I'm using the XLSX package to bring this in from Excel. So just to recap, you have your read.xlsx file being saved to the object name. You give it the file that you want to bring in, the sheet, the rows, the columns, and tell it that you have a header, and run that code. And boom, you have data. So just to look back at this data frame again is fake data. I just came up with numbers that sort of somewhat make some sense, but they're not actual data. So this is just pretending that there was a study that measured some information for 5 tree species, so height, diameter, and average leaf length, and then looked at whether or not a bird's nest was present somewhere in the tree. So that's where this nest presence column comes in. Again, it's just fake data. Now, let's say we want to break this down and we only want to look at the data from certain tree species, or only specific trees that are at least a certain size, or only trees that do or don't have a bird's nest in them. This is where the subset command comes in, and I find this to be an extremely useful way to break down your data and to sort it conditionally, especially if you have a massive data set, which we as scientists often do. Especially if you have really, really big data with lots of data points over time or across a large area or whatever it may be. So the subset command is in base R, so you don't need a package for it. And it is a little bit more complex than some of the other commands that we've done, but it's only complex in the kind of the way that you write it out is a little bit different. It's really not that difficult. Before we look at that, though, we do need to understand how the conditions are defined in R. So we use conditions to tell R that we want specific things to be true about our data that we're trying to pull out. And they're defined by various operators, similar to the assignment operator, which is the little arrow that we use to make objects. Now, it works a little differently than the assignment arrow, of course, because the assignment arrow is doing something specifically. It is making objects. So a lot of these operators are mathematical. So you have equals, the in equal to, so like an inequality, greater than, less than, etc. And you can even use these somewhat to specify exact matches with character values. So let's take a look at them. To do an equality, where you say this must equal this, you have to use a double equal sign. Most of these have 2 pieces to them, just to be specific that it's an operator. This one especially, because some people like to make objects using a single equal sign instead of the assignment operator, which again can kind of cause some problems with R's ability to read it as a numeric. I don't know the exact details of it, but I do know it can be kind of glitchy if you do it that way, so do that at your own risk. But if you're using it as an operator, you should be using a double equal sign. Now, if you want to negate that, or really negate any of them, you replace the first one with, actually, I'm not going to do this in a chunk. I'm just going to do it out here. So equals equals is your equality. If you want to make this an inequality and say basically anything but this, you would have an exclamation mark before the equal sign. So this is saying, if you want anything but 4, you'd put in equal to 4. So this is the inequality operator. Now, greater than and less than are the same as normal. Not sure why that turned green. It might be trying to do something in the document. And then you can also do greater than or equal to and less than or equal to simply by adding an equal sign after those. So something like that. So I'm just going to abbreviate greater than, less than, greater than or equal to, and less than or equal to. Now, there are more operators than this. These are the simplest ones. Sometimes certain commands can be negated by using just an exclamation mark. That is kind of the universal sign of we don't want this, anything but this, the opposite of this, etc. I'm not going to get into that too much. It doesn't really apply here, and it is a little bit too complex to make it generalized. You'll also possibly come across something called the match operator, which is shown by a percent in percent. This is a little bit trickier to understand, and it kind of takes some practice to get used to how it works. But in terms of subsets, like the simplest way to use it is to specify that it can be this and this or this. So it's like an and or almost. I'll give you an example. It'll make a little bit more sense than me just trying to explain it here. But I will show you an example in a minute. So let's get into doing the subsets. I'm just going to make a new code chunk here. So again, let's say we want to look at only one species. And we'll look at one of my favorite species, Q or Quercus velutina, which is black oak. It's a very common tree in the eastern US. And so to do this, we can make a new object. This will make it its own data frame. It's a smaller subset of the main data frame. So we'll just say oak. We'll just call it oak. And so we can do just the subset command. And then we just tell it what we're subsetting. So this is the main data frame called data. And the next technically argument. So this is technically the X argument. You don't really need it as long as that goes first, or if you define all the others. And then you can define the subset argument, which equals, and then in parentheses. This is kind of the weird part about the subset command, is usually this part goes in parentheses just so that the operators work properly. Sometimes if you don't nest them in parentheses, it might do something different. So subset equals, and then in parentheses, then you give it your conditions. So you have to specify, first of all, which column you're talking about. You can only do this by one column at a time. So we want to use the scientific name column. So I believe you need to also specify, actually I don't think you need to specify that it's within the data, because it tells you, you're telling it here. So you shouldn't need to say data $this. It should just be scientific name. And then we want to say equals equals, and then in quotes because it's a character vector or character object, Q velutina. And then you close both sets of parentheses. And what we should get, if I did this correctly, when you run that, is a subset of 10, which is how many we should have, all Quercus velutina. And so this keeps all of these pieces together in each column. They're all assigned to the same value. You have the same tree number, the same height, dBH, etc. for this oak. Now, you can also use multiple conditions. Let's say you want to subset this further into an even smaller data set by using multiple conditions. If you want to do that, you can simply use other kind of operators. I forget the technical name for these, but there's other kind of operators that work as and, which is just an ampersand, or, which is the pipe. Now the pipe is usually on the same key as the backslash on most keyboards. Usually it's near the enter or return button, but it's kind of like a straight slash, and that indicates or. So the ampersand is and, which is typical, and then or for the pipe. There are other uses for the pipe, but I don't think I ever have used that for anything else. But in conditionals, this can mean you want either the oak or something that's not the oak but meets a different condition. In this case, we want the ampersand, and you do this within the inner parentheses for subset. Now you can do it If you put the ampersand on the same line, I think you can put it on the next line down. And this should work just fine, or you can leave them on the same line. Again, I like a lot of spacing in my code because I think it makes it look neater, but some people don't care about that or prefer it the other way, so it's up to you. I'm going to put it on the next line. So let's say we want oak, and it needs to be of a DBH, diameter breast height, of greater than 60 centimeters, which would split this roughly in half, maybe 1/3, 2/3. So DBH, and we want, let's say, greater than or equal to 60. And that should do it. So now if we take this, and it will overwrite the oak data frame. So now we only have 4, yeah. And they're all greater than or equal to 60. Let's verify that that actually worked. Let's just take this. I should have kept it up here actually. So we'll make it the original one, which is just separating out by oak, and yep, so 1, 2, 3, and 4. Yep, there are 4 that are greater than 60 dBH, and then if we further subset it, now we have 4. So cool, now we can subset by multiple conditions. So now let's look at the match operator just as a quick example of how it might be used in this situation. Usually it's used for slightly different kind of situations, but I think this is probably the easiest way to explain it. I believe that it's kind of like using concatenate, because if you were to say scientific name equals C, like the concatenate command, with Quercus, and then let's say a rubrum, it would look for things that have both of those in the name, which doesn't exist because they're 2 different species, so they're all on different rows. So let's say we wanted oak and birch, which is the next species down on this list, below maple, B. elegantiniensis. So you could do this and say subset data by the subset, which equals scientific name matches. So this is saying it matches any in this concatenation. And if you had like a list of species you wanted to pull out, then you could, as long as it was in the same format as this, so characters of Q underscore velutina or B underscore elegantiniensis, you could put a vector of those characters here instead. But we're just going to kind of create a 2-part vector with Q velutina and B elegantiniensis. I think I spelled that right. Yep. Within the subset. So that should, using the match operator, that should tell it that you will want all of the oaks and all of the birches. And now we have 20, which is what we expect. So B. elegantiniensis and Q. velutina. Beautiful. So that's kind of how the match operator works. It's a little tricky to get the hang of sometimes because in other contexts it's not quite this straightforward. But I think in subsetting it does help, because to do this alternatively, you would have to specify scientific name equals this, and you have to put a pipe and say, well, actually, yeah, you'd have to make 2 different subsets and then put them together if you wanted to do it that way. Because if you say pipe, you're going to say you either want oak or birch, which are not mutually exclusive. So I'm not actually sure how that would work out. But feel free to play around with all these different operators. Again, there are more than this, and I think there is a way, if you redefine the function of the match operator, to negate it. But there are plenty of other operators. There are ones that work with matrices and vectors for mathematical functions, like matrix multiplication. Those exist as well. Okay. So let's also pretend, just for another example, let's say we want a subset of the main data frame where you only get the data from the trees that have birds' nests in them. Let's say you're doing a study on, what trees are most preferred by birds for nesting. So we'll say, we'll call this with birds, and we'll just make a subset of data. The subset is going to be, I believe it's called nest pres. Yep. Nest pres equals true. And again, this can be T or true. It should detect it either way, even if you have it differently in the actual data. Note that if you're using ones or zeros, you can also just do that, but it might think that it's a numeric or a character, so be aware of that. Ones or zeros, or yeses and nos. Yes and no or Y and N would definitely be a character, so you'd have to put it in quotes. But using true false, it shouldn't matter if you just use T or F or just true false. It should still work. So this should make, oops, what happened? Did I do something wrong? From the main data frame, subset data, subset equals nest pres equals true. Now that is interesting. Maybe, I bet what happened is it thinks that it's a character. Let's try that. That worked. See, this is the problem if you don't know what class you have in your data. I think because it doesn't explicitly say true or false in the Excel document, that it might not realize that that is true false as a logical. So you can either do it this way, which works just fine to still get it out, or you can redefine it within data. So if we wanted to say data $nest pres, so we're calling that specific column, and you just say as dot logical, it's another one of those as commands, and just redefine it as itself, data $nest pres. And it should be fine coercing it. You'll notice it didn't give me any errors because it is T and F. So now if we do this, now it's going to 0 because now it's looking for characters. Whereas if we switch it back to T, now we have the 27 again. So there's 27 trees with nest pres. And you'll notice it changed them to true instead of a T. So that's interesting. But it seems to have worked. So that's a good example of problem solving because of different classes. It's useful to know how to check for those things. Again, I could have used the class command to check to see before I changed it. I just kind of assumed that's what happened, and fixing it doesn't change anything else anyway. So even if I was wrong, it didn't matter. Okay, so now I have this data set. Let's say I'm interested in, which trees birds prefer. I can't tell you just by looking at it if there is one. I just put them in randomly, so there probably isn't any specific distribution. But let's say you wanted that. And now I'm going to continue our discussion of the XLSX package by showing you how to actually write an Excel spreadsheet from R. So we brought the data into R. Now we're sending a subset out as its own document. So if we want to write with birds as a new Excel spreadsheet, we simply use, again, using the XLSX command that we use to bring it in, the package to bring it in, instead of read.xlsx, it's write.xlsx. And you don't need to call it as an object. You don't need to name it because you're saving it outside of R. So it's not going to matter. It's actually going to confuse R. It's like, wait, I thought you wanted me to send this somewhere. So for this, all you need to do is specify which object, in this case, it should always be a data frame if you're writing to Excel, which object you want to do. So we're doing with birds. And then the file, file will be wherever you want to save it. So again, you just have to know where your files are nested and where you want them to go. So for me, it's home, rdocs, rlessons. We'll just call it with birds. And you do need to save it with the extension again. So .xlsx, quote, parenthesis, and there we go. And you'll notice it popped up down here. And if I open it, pulled up in my other window. It's over here. So that's only the 27. You notice that it includes the 50th tree, but it's only 27 rows in Excel. So that worked for us, and that can work for you if you have your own data that you need to write. Now, one last thing before I call this episode done. Let's say you made this and you want to continue working with the birds data set, the subset that you made, but you want to get rid of the tree-based ones and the original data just so that it keeps your working environment clean and doesn't get you mixed up or confused, which I always recommend trying to keep a clean work environment, especially between sessions if you're working on different things. So let's say you only want to get rid of certain objects. To do this, actually you don't even really need a chunk for this. Let's do this in the console because this is not code that we need to save. To do this, we can just use the rm command, which is essentially like using this little broom up here in the top right to clear all of this, except instead of doing all of this, we're just doing one object at a time. So let's say we just want to get rid of rm oak. We don't care about just the oak. We can just get rid of that, and it gets rid of it. Now, I think in order to do multiple, I think you have to list them, I think. And then I think you concatenate, I might be wrong on this, data and oak birch. Oh, okay. Maybe actually just use the list command. Let's try that. No. Oh, they need to be strings. This is not something I do very frequently, but I did want to bring it up because it is possible. I just have forgotten how to do it apparently. Try concatenating now. Okay, so yeah, you need to concatenate them as strings or as characters. So you put them in quotes, concatenate them, and then list equals. That's the argument to rm to get rid of multiple. So you'll notice we're left with just with birds. So I guess I can put this up here just in case you have a hard time reading it down there because of the colors. We had data and we had oak, birch. These are basically just any objects that you want to get rid of specifically without clearing all of them. Okay, and of course if you just want to do one of them, you just need the data, the object name. So it can just be like rm data or rm oak birch without the quotes or anything. That's a little bit confusing. Okay, one last thing. Let's say you had a really, really big data frame that you wanted to save, but you don't need it right now and it's kind of taking up a lot of memory in your environment. You do have to worry about that with really large data. Like if you're working with genetic data, that can sometimes be several gigabytes worth. Or if you're using GIS maps or something like that, they can be really hefty. So let's say you want it, but you want to remove it temporarily so you have the memory to work with other things in the meantime. If you want to save an object, you can save it as its own file in your directory using the save command. And it's just like this write.xlsx thing. You would save like with birds, or this doesn't have to be a data frame though. It can be a map raster, it can be an image, it can be a plot, something like that. Or like a spatial frame, something that is its own kind of data, which obviously I haven't talked about those in my lessons yet, but if you're a little bit more experienced in R, you probably know some of what I'm talking about. So you could do this and you can just give it a file path, except instead of the .xlsx or whatever, let's say I want to save it to this file, you would just give it a name and then a .robj extension. And that will save it as an R object. And then, if you want to load it, all you have to do is define what you want to call it again. So your object once again, and then you use the load command and give it the file path. So you would just do this. Oops. And this saves it outside of R. So obviously I can't run that. I'm not sure why I tried to. This saves it outside of R so that you're not using up your temporary memory up in here, and that might slow it down if you have really big data. So I just wanted to throw those in here at the end now that we're kind of working with importing and exporting data, just in case you happen to be working with large objects. And then once you have it saved, then you always have a fresh copy. So if you do happen to break it or R crashes or something like that, you don't have to worry about going back and regenerating what may have taken hours to generate. So I'm reaching my time limit. So hopefully this has been helpful. The next episode will probably involve my statistical workflow. I did have one piece of this that I didn't quite get to, but I will start with that next time. So thanks for watching.